to this moment, we considered the problems on which quantum computers perform significantly better than classical ones. Now, this may have a look of unfair advertising, because you may believe that quantum computers are always better. Unfortunately, this is not the case. And in this lecture, we will examine the problem on which the quantum computers are almost as ineffective as classical ones. Let's consider all the functions of this type, which map n-bit integers to 1 bit. Then, for any such function, we can introduce this value. It is actually a very long bit of strings, string of bits. It has n big bits, which is 2 to the power n small here. And for any index here, xj equals to the value of function on this value j. And j runs from 0 to n minus 1. So this is our very long string of bits. And we introduce the quantum oracle, as we do always. We do it the same way as always. And for example, if we put some index j here, like uf of j, y, it will be j y XOR 1. And this means that f of j equals to 1, so we can put xj here, which is 1, plus 1 minus xj, again j, and y. So if xj equals to 1, then we have this part here, and this goes to 0. And if xj equals to 0, then this part stays, and this goes away. Now we can notice that if we apply the oracle uf t times, then any of these states, any of these basis vectors, will have a polynomial of power t of these xj's with different indices before each state vector. Now let's introduce the following notation. Xy wave is 1 minus 2 xy, xi. And let's consider such function parity, which maps functions to 1 bit. So it accepts the parameter this n-bit string, 0, etc. This long string of function values, and it computes the product, and it returns 1 if among these values there are even number of ones, and in other case it returns minus 1. So the question is, if we have a function which maps n-bit integers to 1 bit, And this function is implemented as an oracle, as a black box. How much would it cost us to compute its parity? And in classical case, the answer is obvious. We have to try all the function values. We have to compute all the function values, then multiply them. Maybe with, so the classical complexity is not even O big of n, but just n and big. And maybe with the quantum black box, we can do better. Let's see. So we have the quantum oracle, and we have designed some algorithm which is effective, and it gives us an answer if the oracle function is even or not in T queries to this oracle, quantum oracle. And let T be less than n divided by 2, so it is at least twice as effective as the classical algorithm. So after T queries to the oracle, each state would have a coefficient, a polynomial of the power T of this x. And if we measure this result, then the probability of measurement would be the polynomial of power 2t, because we square each coefficient before the state if we want to compute the probability. Now, some of these states are markers that the function is even for us. So if we measure these states, we say that the function is even, and the sum of all these probabilities of these markers we will call p even. It is a polynomial of the power 2t. So it is the probability for us to say that the function is even, and it depends on the function, of course. Now let's consider this expression. We take this probability of the function, of the answer that the function is even, multiplied by the real parity of the function, and we take the sum over all possible functions. Let's split this sum by some random index, like this. This sum is over all the functions for which xj equals to 1. And the coefficient before the sum is 1, and the sum over all functions for which xj equals to -1. Again, pair even, etc. Product over I not equal to j, xi. And we have this minus before this sum, because we removed this index from here, and this index gives us this minus. And let's look at this sum. So the polynomials here are of the power 2t, which is less than n. So we can choose this index j here. For any monom in these polynomials, we can choose this index j. such as it is not contained in these monoms. And in this case, these sums become equal. And since we can do it for any monom, since the power of the polynomial is less than n, and we have n big of possible indexes, all this sum appears to be 0. Now let's, we already know that this sum is 0. Let's split it another way. Let's split it by even and not even functions. So this x, such as x is even, and we have this polynomial here, and this product for even functions is 1, and sum over x, which is, say, odd, again the same polynomial, and this product for odd functions is -1, so the minus here. And we see now that the probability for us to say that a function is even equals to probability for us to say that a function is odd if 2t is less than n. So we can't be sure, we can't say anything concrete about this function if we make this number of iterations, which means that quantum computers cannot outperform classical ones on this task, cannot outperform. In this case, they cannot perform twice better, twice as good as the classical algorithms. With this optimistic result, we finish our course, the Introduction to Quantum Computing. This was tough and long, still I hope enjoyable road. Thank you all for your attention and participation. The course team wishes you luck in your further research and study and welcomes you to the other courses of St. Petersburg State University. Goodbye.